Hey, Brian, what's up?
Hey, Adam.
Oh, what's this?
Adam, what are you doing? Adam!
No!
Hey everybody, I'm back. Wow, just got snapped away and snapped right back, just like boom, boom, we're back. Be the first, maybe there, I don't know, are there already stats creators on TikTok? I don't know. We got a lot of things going on. We got, you see, I'm mostly set up for like live streaming. TikTok, you gotta do all different stuff. Gotta grab that iPhone with your purple and pink case. Got that iPhone, you gotta be like, hey everybody, TikTok here. Gotta be I'm like such a boomer. Soon people are gonna be like, oh, you're such a millennial. Like, it's going to become the old person term to say millennial. Be like, boomer, that's my grandparents. Probably is. Oh, gosh, I'm getting old. I've heard people, like, say, like, millennial is, like, an old person thing. Good to see you here, Walker. Good to see you here, Matthew. Good to see you here, Max. Good to see you here, Cole. Who all is in the chat? Say, hey, let's grab another 100 points right here while we're at it. Can't leave the Infinity Gauntlet just lying around like that. Shaking. I know. We just leave it on chairs. It's just around the office. Infinity Gauntlet lying around. Just, what you going to do? What you gonna do when the Infinity Gauntlet comes for you? Gone is what you're gonna do. Disappear. I should make it'd be really hard to make that effect live. Like the smash effect, literally I showed Chelsea, I was like, this took 5 hours. It took 5 hours to do. That took about 5 hours to create. Like there's a lot of moving elements to that, like the lens flare, the different backgrounds. Like I just want you to see something real quick and then we'll get serious here. If you watch the background actually moves and the text actually tilts. Can we do some of this week's weekly assignment disappear? We've done some of it during office hours. I'll play it one more time, then we're going to get serious. Just so you can see this. Okay. That took more time than it was worth just to make a smash effect, but you gotta have it. Anyways, we did some of the assignment during office hours today, and we do have office hours in the afternoon. Who wants to come by office hours today and start asking questions about the assignment? I'll tell you this much. I will work at least 2 questions in full. Who's going to be the hero of the day? Who's going to swing by office hours and be like, hey, Brian, could you talk about this question right here? I'm kind of stuck on this question. Who wants to be that person right here to help out? Anyone interested in doing that? We have office hours coming up here after this class. We'll go through and work some of the assignment, talking about it. Anybody? Bueller, Nathan will be there. Don't worry, Daniel. We're going to have people asking some questions. And so just drop those questions. Remember, we have office hours in the morning, in the afternoon. I realized next semester I'm going to try to advertise them more because it's all right. I'm like, 320. We had someone show up from 320 today, asked some questions, and we talked over the strength of the relationship between homeowners and non-homeowners and looked at those graphics. So let's jump into the notes right here. We might, you know what? We'll try to do a question at the end of class today. How's that sound, everybody? What does chat think? Should we do a question at the end of class today? Maybe talk over a little bit about the assignment, a little bit. Maybe we'll do it towards the end with the logistic. Maybe not. I don't know. Your call. We got new music too. Found some new music during Stats 1 yesterday. Your thoughts? People are saying yes. Make that happen. People are saying. That would make your day, Cole. Well, we're going to make your day, Cole. We got some new material. We got new music. So much going on right here. Let's hop into this. New material here. Do we have the right slides up? We don't even have the right slides up. Watch out. Here we go. Material time. There we go. Slides up and going. Wake up, Ben, right there. Ben's got to wake up so we can do that assignment. Let me take off the calculator on the screen. Good stuff. What? Epic Pen just totally messed up my whole screen. Stuff going on. So when we look at this right here, we're running a logistic. What are the 2 things you notice about running the logistic right here? What are the 2 things you notice about running the logistic right here? You should know this immediately. Repeat this to yourself. You're falling asleep at night and you say, the logistic has 2 differences that we need to do every time we run the logistic. And what do we mean by logistic? We're predicting diabetes. And that is right there, the Y variable of interest, which has levels yes and no. GLM and family earning another 100 points right there. Do monetize family and GLF. Daniel sees it too. Excellent work. And this is a quantitative Y. So the family portion right here, Y tilde X comma data equals family equals binomial, meaning 2-level categorical Y. And we're predicting whether or not someone has diabetes. I don't know. I watched the joke too many times and now I just say it improperly without even meaning to. I just can't speak. Now, what is the level of interest? Yes or no? Quick review. We have to review these things. These are easy questions on the test. Is the level of interest yes or no, and why when we're predicting this variable right here? Great job, Wilton, right there. Another 100 points. It is yes, and why is it yes? And we can also tell this if we look at a model. Pretty easy to tell with any model that actually shows it, if we can visualize it. Oh, wait. Oh, what's the probability of no? Oh, because this is donate. This one has donate and donate no, so that is correct. And this one, tricked myself. This one has donate and no. So it's not donate yes and no. Well, you got to say it in Spanish now, Nathan. I have no idea how to say it in Spanish, so you're going to have to put it in the chat. So this one has donate and no, and we're predicting no. You might say, I thought we were predicting yes, because the level of interest is last alphabetical, and no, it comes after donate. So does that make sense? Now, diabetes is interesting because it is not interesting. It's because it's yes, no. So this is the one we are going to predict because this is the last alphabetical. And usually people get confused on this because it differs from reference levels, where the reference level, if this was an X variable, would be which? The reference level, like we were just doing in the assignment. The reference level is the what level. Looking at this R output right here, the reference level is the what level. Let me close off. We were talking about the output today. The reference level is the first one. Can you tell, you can watch today's office hours too if you want to go over this, but can you tell which of these has a stronger relationship, no or yes? We were talking over this during office hours. This is not logistic right here, but this is regular regression. Hence, we wouldn't do the GLM because last amount is quantitative. So which of these has a stronger relationship, and how can you tell this? And we go into a much more detailed explanation during office hours, and I was so happy the person was like, yes, I get it. No is stronger because higher slope. Exactly. So does that mean yes has a negative slope? Because I'm looking at this and that doesn't look like a negative slope to me. Like this slope right here doesn't look negative. And great job, Daniel, right there. Excellent work. Notes, perfect answers right there in the chat. That slope doesn't look negative to me though. Like the homeowner, yes, recent average amount interaction, I don't see a negative slope. So I'm like, something's wrong right here. This output doesn't look accurate because this is negative. So what does this negative mean for recent average amount homeowner interaction when you see this negative interaction right here? Which is, we're going to start talking about interactions more in a second with logistic. What does that interaction right here mean? Like, we can solve the equations, and the equations might give us good information. But think about when you look at the no line and the yes line. Well, so recent average amount has a positive relationship at all points. And so, Daniel, you're on the right track right there. The original slope is this. Does that make sense? Exactly. David said it perfectly right there. Both great answers, both of you right there. More points in the chat. David said that the slope of the yes line is 0.17. I rounded up right there. Is 0.17 lower than the slope for the no line. It's a stronger relationship, not correlation so much, but a steeper slope. Does that make sense? The steeper slope indicates kind of a stronger relationship. The weakest relationship, so it's not quite correlation, but the weakest relationship would be a flat relationship. The steeper the relationship, kind of the more changes we see in X and Y mathematically. So there's a stronger relationship right here where values of X would change the value of Y quicker on the black line than the red line because the black line is steeper. Does that make sense, Cole, right there? Exactly. Daniel, perfect. Did great job. Great clarification right there. It's still a positive relationship, but it's weaker, and it's weaker by this amount, which is a statistically significant interaction right here. It brings with it new information not accounted for by the other variables. 100 points. Great job. Great conversation about what these interactions means. Kind of, sort of, Nathan. Like, I'm not saying, but kind of, sort of. Kind of, sort of. And we were talking about there with categorical X's, which include reference levels. Kind of, sort of giving away some answers. Maybe come to class, hashtag show up, get some answers. Here we are with our model. Let's go into our new topic for today because we've talked about significance. And once again, when we do an LM, we're fitting a what to the model. When we are fitting an LM, we are fitting a what to a model. And there's other ways of doing this, but when we do an LM, what are we fitting to a model? Like, these are examples of LMs right here, where you're doing different implicit lines by solving in the value of x2 and then solving out the equation, which would change the intercept. So you see here, by plugging in these values for x2, you would just get a constant, and that constant would change the intercept. So the changes to the intercepts noted here, here, and here are just differences of values of x2. And look, the coefficient is 2, And thus, when you change it by units of 1, you're changing by units of 2. So you see a 2-unit difference right here when you change x2 by 1 unit. So what are we fitting with the LM? It's implicit or implied in the LM. What are we fitting with the LM? And I'm going to ask a trick question. 100 points on the table right now. What are we fitting with the LM? We are fitting a what? We are always fitting this with the LM. What are we fitting with the LM? With LM, we are fitting a what? It's what LM stands for. A line right there. We're fitting the line, the linear model, and that's what LM stands for, is linear model. So we have to be fitting a line. Now, here's the trick question, though. When we fit a GLM, what are we fitting? And we can actually fit a line, and that's actually the default. But when we choose family binomial, that's where we get the change. The family binomial fits the logistic curve, so I kind of answered my own trick question. A great linear GLM stand, what's in right there? So it stands for the generalized linear model. It's more, it's not just so like linear model is like only linear models. GLM is the generalized linear model, which has more versions of it. So a weird word that starts with S, sigmoidal curve. So we can fit the sigmoidal curve, which stands for S-shaped curve. And truthfully, let's go take a look at this real quick right here. When you're running the GLM, I don't know how many families there are for it. Does it have fitting generalized linear models right here? So take a look. There's the Gaussian, which is the default right here. There's so many more things you can do that we don't do. How you handle NAs. Does it have like a stepwise? I don't know what that is right there. Method, GLM fit. So all these different things right here. Family, all the different families you could pick from. Binomial, Gaussian, gamma, inverse Gaussian, Poisson, quasi-binomial, quasi-Poisson. So all these great things right here, which I've only really worked with the binomial, the Gaussian. I've done some Poisson, I guess a little bit of gamma. Inverse Gaussian. There you go. It's the inverse normal curve. But I've never really worked with that one or the quasis. But all these different ones right here are different things we can do and reading through. Some AIC. We'll mention that later on. But all this good stuff right here are things we can do with fitting the curve and the GLM, which is the generalized linear form. So it just allows for more kind of fitting options for us. And that's how we can get this right here with the family equals binomial. The beta linear curve versus the sigmoidal sigma. I guess Kraken's jokes in the chat. Back in my day, all the models were linear. This new hippy dippy curve models is what's wrong with our new. Max, I like Max jokes the best. Max got a good joke right here. We'll put that in as a joke. Should that be a joke right here? I think that should be a joke. Let's go here to extra quotes. Max, we need more jokes in the class. That is now joke number 9, Max. You now have joke number 9 right here. Joke number 9 in the books for Max right there. We talked about statistical significance last class. This is kind of a review. I was like doing a little review, but let's hop here, if it lets me click on it, down to the interactions and categorical variables. So when we have these interactions right here, thank you, Daniel, right there, checking in on our new jokes. So we have the interactions and categorical variables and how these work. We're getting into the second assignment right here. So when we predict the probability of something, the probability of a y variable, what did we say we were fitting to the models for the GLM? Oh, we're fitting a sigmoidal S-shaped curve. So Daniel, good question right there, Daniel, and make sure I was trying to answer all the questions. We're fitting a sigmoidal S-shaped curve. Does that make sense? We're not fitting a line like we used to. We're fitting the sigmoidal S-shaped curve. So it's a sigmoidal S-shaped curve, sigmoidal. Sigmoidal just means S-shaped. You could just say nonlinear curve that bends through the data. And it's trapped, contained within 0 and 1. Great question, Daniel. Thank you so much. Crazy points today. So with this interaction right here, the probability of y and the way in which x1 explains it might depend on x2. So we're seeing right here with an interaction, no longer is it a constant sigmoidal curve. What might happen? Well, for different values of x2, x1 might be flatter. And we'll see this right here. So with a positive interaction right here, we're going to see a stronger curve, or a negative interaction, we're going to see a weaker curve. Does that make sense? So let's take a look at some of these values right here. And here we have that the interaction is what? Just tell me positive or negative. The interaction term right here is clearly what? And look, they're both negative to start. Ooh, so that's interesting. So we see, yeah, makes sense. So we see here it's positive. Great job right there. Following along points right there. We see that there is a positive interaction. So the original curve is negative. And so let's go down here to the value of x2 at the smallest value. And so this is kind of the smallest. And what's weird, and you got to watch out, and this is the strongest. Even though this interaction is positive, be careful. As the values of x2 increase, the relationship x1 actually has gets wetter. As x2 increases from smallest to largest, strongest, or I said, did I say strongest? What did I write? My gosh. It's largest. It's not strongest. Largest. So as it increases from smallest to largest value, so this is large. Whoops. Yeah, no, this is large right here. Oh, it's out of, why did it do that? That order is ridiculous. That order's not right. Didn't put them in order. Not cool. Not cool. So what do you notice about the relationship as it goes from smallest to largest? And then why is it this way? As the value of x2 increases from smallest to largest, the relationship actually gets wetter. Exactly, it gets weaker. Great job, Josh and Wilton, right there. Some points. It gets weaker. Now, why is this? Because the relationship x1 has is what to begin with. The relationship x1 has is what to begin with. So the relationship x1 has right here is what to begin with. x1's relationship is what to begin with. It's negative. x1's relationship is negative to begin with. So since x1's relationship is negative, going through these values right here at first, and you have to look at the vector by which you're going through, if this is what we're contained in, going from the smallest values of x2, which actually start out very negative, make it even stronger, because that's going to be a negative and a negative right here when you do the negatives. So you're going to get a very strong relationship down here for the negative values. That's this one right here. And then when you go up to the highest values, which is this one, I wish it went in order. When you go up to the highest values of x2, you actually get the weakest. So this is the weakest relationship right here. Now, if there were more values, eventually it would start to go positive and it would change the nature of the relationship. But notice right here, what does the logit p mean? That is actually what we're solving right here if you solve out the general equation. Now, we don't solve for the logit of p, and I really don't even interpret it. I don't like interpreting the logit. I don't think it's good interpretations. So if someone were to solve this right here, what would you do with this value that you just solved for? Let me highlight it in a different color. If you solve for the logit of p, which we'll never, it won't be on a test. And Max, thank you. Great question right there. If you were to solve for the logit of p, and you were to get this value right here, what would you do with that value? So when you solve this equation now, what would you do with that value? And there's what we're going to do with it right there. Exactly. David said so perfectly. David, another 100 points right there. David said we're going to just plug it into the e raised to the, Lisa, great job there too. Plug it into the e raised to the over the 1 plus e raised to the. So when you get the logit of p, it's really just a proxy for what you're going to be plugging in to the equation right here in both spots. And that's where I just say e raised to the x over 1 plus e raised to the x. And make sure to do this, like, seriously, this is what people get wrong on the test. People don't realize that logistic is different. You must be solving probabilities. How do you know when you've solved this right here, if you've solved it correctly? Anything you do on the test with logistic, when you solve it, must solve for what? 100-point question. I've been throwing crazy points these days. Anything you solve on the test must solve between 0 and 1. Any answer you get must be contained between 0 and 1. And if you get something, whoops, contained, it could be this. If you get something like 1.28, you probably didn't do it proper. That doesn't mean 1.28%. It probably means, and that would be like a 0.6 or something probability, but you're getting probabilities right here, so you can't get values outside of this 0-1 boundary right here, which you can see. And if you get a weird number, like especially negative, well, that means less than 50%. So your P right here, probability will be something like 0.38 or something because it's negative, which means it solves out for not the level of interest. And we've covered that a good bit, but please make sure to solve out the logistic. And if this doesn't make sense, review where we've been solving logistic equations. Same sort of thing with interpretations, but let's look at this. What do you think about when it comes to diabetes? And we have here insulin and glucose. If someone has high glucose, what would that do to their probability of having diabetes? If someone had high glucose, all you have to look at this. Two individuals who are otherwise identical but differ in their glucose by 1, the person who has higher glucose would be expected to what? Two individuals who are otherwise identical, it's going to increase higher probability. Exactly. Great job right there following along. Two individuals who are otherwise identical but differ in their glucose by 1 unit, the person with higher glucose is expected to have higher probability of diabetes, would have a higher probability mathematically. But what do you notice about the coefficient of the interaction? The coefficient of the interaction for either of these is what? Which means even though we're saying higher probability, then what's going to happen when the other one's higher? This is where it's interesting. And everything here is statistically significant, which is good. This is real data once again. This is from the PIMA data. This is a tribe right here. They're examining diabetes among the women. And what do you notice about the interaction? The coefficient is 0.005 or 0.001. Which one? Oh, this coefficient right here. And remember, we don't interpret the coefficients here. We only look at the sign. This coefficient is point, and you count the leading zero as the first zero. That's 0.05, and that's 0.013. And this one is negative 0.00007. The interaction is negative. The interaction is negative. So the interaction is negative even though individually they are positive. Correct. So let's take a look at the implicit sigmoidal curves. There'll no longer be implicit lines right here. We'll get implicit sigmoidal curves. And take a look. At very high levels of glucose, so if you have very high glucose, what would be a good thing to have that would probably make you less likely to have diabetes? What would be a very good thing to have? If you have very high glucose, what would be a good thing to have? Just think about it logically. Just go with logic right here. Don't even look at the graphic. You would want high insulin. So these individuals right here with very high glucose, these are 4 individuals with very high glucose. At this point, 2 individuals who differ in their insulin by 1 unit, the person with higher insulin but also has high glucose, these people with high glucose, everything's identical between them. They both have high glucose. The person with higher insulin would be less likely, I can't draw on it for some reason, would be less likely to have diabetes. That's what's important right here. But where are you in the really bad scenario is if you have very low glucose, that says glucose small for the blue line. And this is where we see one of the strongest relationships where for people with very low levels of glucose, insulin would do what to their probability of diabetes? For people with very low glucose, now we see a total change in the relationship right here to kind of its original form. Now it's going to be increase. So when we have 2 individuals who both have very low levels of glucose, we would expect people with higher levels of glucose to have a higher probability of diabetes. Could you explain what it means in general when the interaction is negative versus when it is positive? So you kind of want to think about how the data is originally. The original relationship right here, such a great question, Max, right there, 100 points, Max. The original relationship of, let's say, because we're doing glucose right now, we're doing insulin. Let's do insulin and talk about insulin right here. The original coefficient of insulin is what right now? Just very quickly, just look at it and how do we interpret it? Where we'd say 2 individuals who are otherwise identical, but one has higher insulin, the person with higher insulin is expected to have a higher probability of diabetes or would be predicted. So right here, we have a positive relationship. Does that make sense? But now since we see a negative interaction, in these values you can't have negative values of insulin, so we don't have to worry about like, well, what if the signs flip with negative? Now, since we're talking about when people have higher glucose, how does higher glucose impact or change the probability in which insulin predicts having diabetes? Does that make sense? So now, what's going to happen as glucose goes up? The coefficient of insulin would do what? For higher levels of glucose, the coefficient of insulin is going to get water. It's going to decrease it. Does that make sense? It never overcomes it to where it makes a negative relationship. Oh, does it? No, it does actually. I stand corrected. It does overcome it from the negative to positive relationship. Eventually, at some point, you can see right there with the arrows I drew, eventually at some point for very high levels of glucose, it's actually beneficial to a person to have higher levels of insulin. And just think about that from a biological standpoint. Eventually, at a very high level of glucose, your body should have very high levels of insulin because it's like how your body works. It's how your body fixes these things, breaks down glucose with insulin. So the negative relationship, does this help make sense, Max, right here? What we're seeing right here is there is a positive relationship between insulin and the probability of having diabetes, positive sigmoidal curve. But for higher levels of glucose, it's going to make the relationship weaker till eventually at very high levels of glucose, it becomes beneficial. How many implicit sigmoidal curves are there? 100-point question. How many, can you explain the 3 lines? That's where we're going with this right here, Josh. How many different lines are there possible, or sigmoidal curves? Because these are not technically lines, they're sigmoidal S-shaped curves. So how many different ones are there? Since in logistic it changes like the sigmoidal bend. So I wouldn't call it slope so much, Daniel. I would call it the sigmoidal bend. Like, it is kind of a slope coefficient, but it's a sigmoidal bend. Does that make sense? Like, because these all make S-shaped curves. So the sigmoidal bend is controlled by the coefficient. Does that help make sense of that? And how many of these possible sigmoidal bends are there? I wish I had an animation to show this. I could almost do it. Oh, I could almost do it. It would just take too long. It would take like 10 minutes at least. I could make you an animation that shows this, I think. How many different sigmoidal curves are there? How many different sigmoidal curves are there? Who knows the answer to that? Oh, I feel like I could do it. How many different sigmoidal curves are there? Like, what I'm asking is, how many different theoretical values of glucose could I plug in? How many different values of glucose could I plug in to solve out the equation and make implicit sigmoidal curves? Not just levels, but since glucose is David, good guess right there, good attempt. Not just levels, and Max, you're close with a ton. The answer is infinite. So the curve would bend through this. Does that make sense? As you go from the lower level, do you see, like, I wish I could show you this animation that when you go from a low level of glucose to higher and higher levels, the curve changes. So it's not like there's 3 lines right here. These are just 3 values we're solving for. What we're doing is we're plugging in numbers and solving out for 3 different values of x2. So we're solving out for like a low value, a medium value, and a high value, but there's infinite curves between this. Does that help make sense of what we're viewing right here? We're viewing 3 possibilities, but there is a possibility that is a flat line because it would go through that. It would go from this into this. So there exists at some point a relationship where there's a very flat relationship. So there... a ton of... I think Walker's here right there. Great job, Walker. 100 points. So these are just 3 possibilities. So it just depends on the code if it breaks it down into 3. Yeah, that's and that's why Peter coded this, is to show 3 different versions. And I know I could. I don't think we should spend 10 minutes of class times where Brian creates a shiny app to draw this. I just want to make it. I want to make it. I love making graphics. One of my favorite things to do. It's a fun kind of artistic, creative thing to do. But maybe I'll do that like. Maybe if we have time during afternoon office hours, I'll make a shiny app that shows you all possibilities where we could just shift it over by changing it. So these are just 3 random perfect answer, Cole. Those are just 3 random test values. I think it's found from the 10th percentile, the 50th percentile, and the 90th percentile. So anything is possible. We were just representing like 3 exactly, and we're using a small value. Great job, Walker. Although also some more points in the chat. We're using a small value, a medium value, and a large value to say like, well, these are people who have lower levels, these are people who have the medium level, and these are people at the large level. So we're doing like different ends of the spectrum. Does that make sense? Walker said it very well with like 3 tested values, or Cole said it there too. Does that make more sense? Like, we're just saying like, let's draw 3 of these possible lines and just look at what's going on. Let's use a small value of glucose, a medium value of glucose, and a large value of glucose. And thank you everyone for pausing, because we should understand what is this graphic conveying to us. It's just showing us 3 values of plugging in values of glucose and what do we get for an equation. And it lets us understand going from like small values to large values, what do we see? And going from a small value to large value, we see actually a change in the relationship. And that's due to the interaction. That is 100% due to the interaction. So really good discussion there, everyone. That's what we're here to do. What do you notice right here? Once again, the original coefficients are what? Same sort of deal with this. We're seeing the same deal. The original coefficients are what? And you see it right there. Joshua's getting right to the meat of it. You got it, Joshua. We're going to have some steak for dinner tonight. Tacos last night, steak tonight. Meat of the thing right there. We got it. Original coefficient is positive, interaction is negative. Exactly. So at small values of insulin, BMI should have a what relationship? At very small values of insulin, we should see BMI having a what relationship? At small values of insulin, like if insulin were to equal to 0, smallest value. At small values of insulin, BMI should have a what relationship? This would just zero it out. The interaction wouldn't exist then. Should have a positive. Does that... Who's following me? If I say, if you plug in 0 for insulin right here, the interaction just goes away. Because if you plug in 0, the interaction term,
it doesn't matter.
You know it. Who's following me on that right there? So then it just has a positive relationship. And 0 is the lowest value of insulin you could have by insulin being restricted to positive numbers. So we should see a positive relationship with insulin for very small values of BMI, or vice versa. And then when one of the variables increases, it's going to make the relationship whatter. So it's going to make, when one of these variables increases for larger values, it's going to make the relationship whatter. The interaction is going to make it whatter. I know, man, those are some... It's going to make it smaller, going to make it weaker right here. It's going to make it weaker. Let's go look at that. And what do you notice? Very small levels, the strongest relationship. And then as the curve changes, it gets weaker, and eventually it goes negative. So eventually, great job, Walker and everyone, Nathan following along right there. So it starts out positive for very small values of insulin. That says insulin small right there. So small values of insulin, strong relationship. And as we go through higher and higher values, it gets weaker till the point at which it actually becomes negative. So remember, there are infinite curves right here. I just want to develop this. I think it's a really good thing to see, but you'd watch 10 minutes of me coding to see probably 10 minutes of me messing around with the app. So I just feel like it wouldn't be that hard. I'm like, could I do it in 5 minutes? I don't know. Maybe we'll do some Hackerman at the end. So now we could also do interactions on what variables? What kind of variables are we looking at right here where we have this sort of X variable? Be very careful. We have what variables being incorporated now? What kind of variables are we including now? Very important. Categorical, and we're going to have reference levels right here. So we need to make sure, what about the lurking variable when taking insulin in small... Ooh. Daniel, these are the great concerns. What was this data collected and their lurking variables? Daniel, great comments right there. Yeah, Daniel, we need to look into that. So really good questions right there. Lurking variable, if you think it's a lurking variable, you put it in the model and see if it attributes to the variation. So that's what we would do. Great question. That's how you handle lurking variables. So here we are. We have a reference level. Let's take a look. And what do you notice right here? Is there an interaction? How could you tell if this model had an interaction or not on it? How could you tell if this model had an interaction or not? What would you expect to be different if there was an interaction here? If there is an interaction, you would expect what? Just look at this and be like, is there an interaction right here? So this is predicting whether or not somebody will leave their cell phone carrier. We have people who have an international plan, yes, international plan, no, and Wilton is correct. And Wilton, why do you think there's no interaction? You're totally on track with that. What you actually see right here is a change in the model. And you're seeing a change in what? Now, this is interesting because this is where 50% is. And remember, negative B0 over B1. So this has actually remained constant. That is no change. But what actually did change? Correct, Wilton and Daniel. You are correct on that. 100 points out there. So what actually did change? What actually did change about this? The sigmoidal shape did not change, which is the coefficient of the slope, coefficient of the x. But what actually did change, which changes the ratio then, which changes the 50-50 breakpoint? The intercept. So this is actually what you're seeing changing right here about this model. It is a change to the intercept, because remember, this ratio right here gives you where the 50-50 breakpoint is. So because the intercept is different, it changes the point at which we change the prediction. So it kind of moves the curve over. Does everyone see that? The curve is moving over by this much unit difference, because the intercept is changing the 50-50 breakpoint right here. So the intercept has changed, but the slope, sigmoidal shape coefficient, like if we want to be exact, we'll call it sigmoidal shape coefficient, is what's not changing. And that's the actual bend of the curve. Let's go change that over here. Let's go change that. There's the coefficients for the model. Let's go change it. Now we have another model right here This model right here has no interactions in it. Fun, fun, fun. Good stuff. Let's go look at, oh yeah, we should mention this. How can we check? It's just more examples. How can we check to see if area is significant? If you look at area classification right here, we definitely need to mention this. Area classification looks like this and why? Why does area classification look like that? Now, area classification has 3 levels. It has rural, suburban, and urban. So what's going on right here? Where's rural? LMNOPQRSTU. Where's rural? Why is rural not there? What is the coefficients for rural? Why is rural missing? These are things when we look at this output, we should know it. Rural is missing. It's the reference level. Boom, right there. We don't have any indicators for the reference. It is when you plug in 0 saying this is not suburban, this is not urban. It's right there. Daniel knows right there. It's the reference level. So we got an interesting problem though right here. Right now we got that this one right here is statistically significant. And this one right here is not statistically significant. So let me ask you this. Is area statistically significant? And what do these things mean? Like, answer either one of those. Question 1, is area statistically significant? If not, what should we do to figure that out? And question 2, what do those p-values mean right there? This is a review because you'll be surprised how much is review. Is area statistically significant, and what do those p-values mean? So who's got ideas on is the idea of area? David right there, great job. Drop 1 is going to let us look at the significance to drop it out of the model, and people are talking about nice job, Whitson too. And Wilton answered the second one. These are the comparison to the reference levels right here. So this, it really, I don't care about any of that. Just we don't, because reference level is arbitrary. So that's in comparison to level R, which is the reference level, ironically here. So we don't really care about those, Rock.
It doesn't matter.
Those don't matter. We're going to go here to a drop 1. Now here's where we have to slow our minds down. The drop 1 has a little bit of a change. Now when we're doing the drop 1 right here, we're going to look at the p-value to see if it is statistically significant. That's all that says right there. I think we know how p-values work. Less than 0.05 statistically significant, greater than or equal to not statistically significant. But when we do this, we have to add in a second argument here. What was this previously? What was this right here previously? When you're doing, and let me put notes on this screen. If you are doing linear models, it'll be quote, and people are saying in the chat, nice, capital F, I believe, right? Someone said capital F, right? So F in the chat, I think that's quote 9. Mubot knows about some F in the chat. And then if you're doing logistic equals quote chi-square. Put in quotes, don't put a bracket around it, parentheses. So quote chi-squared. So we have to switch this up right here. So is area statistically significant? And this is a shocker right here. Because remember the p-values, 1 was a little bit significant. We'll go look at them again. This is 0.9, which is not significant at all. This is 0.01, which is statistically significant. And so is area statistically significant here? Does area bring with it new information not accounted for? Yes or no? And it says it down below. Is area something we should include? Now, age, what do you think? Pretty obvious right here. I would say most definitely include. Exactly. Great job right there, David. No, so it is statistically significant. Area is statistically significant. It does bring with it new information. So this means it does. No, double check Wilton right there. Oh, I might have mentioned something else, but this variable right here is statistically significant. This one is not. Age is not statistically significant. So try to highlight in a red right here. This one is not statistically significant. And then we'll highlight in yellow because yellow seems more like good highlighter. These are statistically significant. We don't have to run p-values on these. If you notice, it's got the stars indicating. Yeah. So, and this isn't like a test where we're checking conditions. We're seeing if these variables bring with them new information. If you didn't know this right now, take a note. Drop 1 sees if variables bring with them information to your model. Does that make sense? Drop 1 sees if including variables brings with them information. So in a drop 1, if you want to include something, or if you're looking to include something, you'd want to see if it has a low p-value. What this indicates to us right here is that maybe age should not be included in this model. It's quite possible age should just be tossed out of the model. We could have just looked at the p-value on age. I think it runs a little bit differently. We don't get the exact same p-values. You see age has a high p-value right here, 0.7959. I hate the scientific notation. Look at that p-value. That's ridiculous. So we get both non-statistical significance in both of these, so age could probably be excluded from the model. But how about those interactions right here? Now, this is where it gets a little bit interesting. Let me ask you this. The relationship checking balance has will be what to predicting if someone makes a purchase? Be careful. Now, the answer is it depends. But it'll be what? I'm solving the equations in my head as we do this. The relationship checking balance has to making a purchase, like how much someone has in their checking balance, to whether or not they make a purchase with us will be what? The relationship checking balance has with making a purchase will be what? We're predicting, does someone make a purchase, yes or no? And purchase is a categorical Y variable, hence the GLM family binomial. Yeah, I'd say strong. Will be positive or negative? Or it'll be positive for one group, negative for another. So it is statistically significant. This variable is, the interaction is statistically significant. The variable itself is not significant. I'll mention more on that in a moment. Well, let me ask that now. Why do you think we should include homeowner yes? What is the argument for including homeowner yes right here? Because this is not significant. So why might someone say, let's remove that? And you say, you know, I'd actually prefer to keep it because I like this. That is not statistically significant. Hierarchy, boom, just right off the bat, hierarchy. Hierarchy says if we have a model with x1 and x2 interaction, we should have x1, x2 themselves in there. So you might say, let's keep a model hierarchy because if we have an interaction with the homeowner yes, we should include the, because volumes. Oh, Max, you're awesome. Love it. Some more points in the chat. Okay. So the relationship right here is going to be what with checking balance at all points. And I'll tell you how I know this. The relationship with checking balance is going to be a what relationship? And you can look at this, like two individuals who differ in their checking balance by $1 or whatever amount. The person with more in their checking balance is what likely to make a purchase. And I'll tell you how I know it's always going to be this. I'll explain. Well, be careful. The coefficient of checking balance is positive. So we're just looking at checking balance's coefficient right here. That's it. So it's a positive relationship. Does that make sense, Joshua, right there? But the interaction, Joshua, 100 points, taking a stab out there. Don't worry, no one was answering, so you got that answer in the chat. But the interaction is what, though? So the interaction, here we'll draw the line. It's going to look something like this right here. We got a positive relationship with checking balance and making a purchase because we're predicting, does someone make a purchase? Yes. So the relationship is positive, but the interaction is negative, correct? But I want you to look at this coefficient. When you plug in homeowner yes, what values will you plug in for homeowner yes? What value would be plugged in here for homeowner yes? There's only two values that could go in for homeowner yes. So the only two values that can go in for homeowner yes are what or what? 0 or 1. So we kind of just wrote the black line right here. And let's do this. Because if we plug in a 1, by default, it'll make a red line. So if we plug in a 1. So now when you think about this, I think, with higher value, but there is no higher values of homeowner. We're going to solve out for homeowner yes, homeowner no, because you are right with checking balance right there. We're going to solve out homeowner yes, homeowner no line, or homeowner yes, homeowner no sigmoidal curve line. And so if you plug in a 1 for homeowner yes, will you get a negative or positive value of checking balance? Now look, they both have the same scientific notation at the end. So will the coefficient of checking balance remain positive, or will this be enough to make it negative? What do you think? They both have the same scientific notation. I know we're dealing with positive but lower. So I'm going to draw the same shape right here, and I think the intercept moves over or so. So I'm going to draw the same shape, but I'm going to make it weaker. Does that make sense what I drew right there? Still positive but weaker. And that's because this is how much it changes by. We're making it weaker right now. It was this, and now it's weaker. And let's go look at this. We should see this. That's what we drew out expecting to see. And there you go. Not exactly it. But look, the red line's weaker. There's the black line. And it's kind of like, well, if you zoom in on this portion, I kind of did. I thought I've seen these slides before. Right over here, if you look in on this, you kind of got that right there. That's kind of that portion of the curve right there. The black line has a stronger relationship, but the red line is there. So the interaction itself is statistically significant. We get that p-value right there, and that's that p-value in green that I've circled. So the interaction does bring with it new information, which is not accounted for by the other variables in the model, so kind of a good thing. Why do we not need to run a partial F right here? What if someone said you should probably run your partial F on this? And would you say, you'd be like The Rock and say, it doesn't matter. Why do we not need to run a partial F on this? Because when do we need to run a partial F? And why does this not apply to partial F? I.e. drop one effects test. It's just one, right? Nathan, great answer right there, 100 points. We're just removing one thing. How can we tell again which one is stronger relationship? We're just looking at the red and the black. How can you tell which one of these is stronger? Imagine you're going out and going sledding with your friends. Here's you. A little sled right here. We're going to draw it. There you go. Sit down on the sled. There we go. You're sitting down on the sled and you're like, I'm going to go sledding right here. Woo! And so which one has the bigger slope? Which of these looks like a more fun hill to sled on? Now, they're not too big of a difference right here, but a little small difference right here. I just got to tell this quick story. When I was a kid, the best sledding experience I ever had was the craziest. There was this hill that we would go down, and it went through someone's yard, and then their yard went over a creek, and they actually made a thing to jump over the creek. And this is like, 10, 15 degree weather. So you actually like went over the little creek, which was probably about, I don't know. It wasn't too big, but if you like missed the thing, you went into the creek and just got like totally wet. And it was like the most fun. You're like, I gotta hit the thing. Cause like if you were like, I'm freezing, you're like, go home. You're gonna get frostbite. You messed up. You didn't hit the ramp and go over the creek. But yeah, that was a crazy fun time. I love it. Oh man. So much fun sledding. Man, get a good sledding hill. Oh, and then we went sledding at UT back in like 2017 or so when we got the big snowstorm. My favorite equation to go sledding down is a constant. You like the linear equations? You like linear hills, not sigmoidal hills? We went sledding at UT one time, and I ran into like a fence and like hurt my, which, is that this finger? This finger's hurt me for a while, but maybe that's why this finger hurts. But yeah, I ran into the fence and my hand hit it. That was a bad idea. Still a fun time. Until I got hurt. We went home and I was like, I hurt my hand. We're going home. Okay. Sledding adventures with Brian right there at UT. So when we are fitting our linear curve, what do we try to optimize with our linear curve? And I'd say there's two things. What two things might you try to optimize with your linear curve? Now there's one you'll hear me talk about all throughout 475 rather, even too. So what might we try to optimize? Let's go take a look at that. I would like you to see something from a class that you have not done yet. Maybe you'll want to take this class one day. I'd be honored if you did. But let's go take a look at this right here. And I'd like you to tell me which one of these models is the best and why. Now, here we'll try to make it look a little bit different because those are all too similar. Well, actually, you could tell me. Which one of these models do you think is best? Model 1, Model 2, Model 3, Model 4, Model 5? Who has a guess of which model do you like is best? And Wilton and other people are getting it right there. Just tell me which model do you think is the best right there. M2. Max, you just did it. You just did a class you've never done. And so you could see right here, we can make one of these models really bad right here. And we're just changing. If you look, wait a minute. What do you notice? Does anyone notice a little thing right here with what's going on right here? Who notices a certain format with this ARIMA thing with the something? No, this one's going to be really bad. First one's going to be horrible. What do you notice here about this format right there? And woo! It's kind of like a naive model. No, kind of naive. It's a white noise model. What do you notice about this? So hopefully this gives you hope for the future. If you want to take like 475, you're like, psh, I can do that. I'm just writing out multiple models. Now we're fitting 5 models. Pretty quickly too, right? So what do you notice about this format? It's the last comment I'm going to pretty much make on this. And Wilton's right. We're looking at the RMSE down here, the root mean square, the typical miss. You are right about the tilde. And what do you see right here? y tilde x, and there's no data because the data is actually being piped into it. More on that if you take 475 on how we're using the piping right here to pass things through. Like the data goes in, creates the models, and then we run this through the accuracy. What's really great about this is we could change what we're doing right here with a report and get a totally different thing at the end of this and get a report here at the end looking at the AICs. This isn't data mining. This is a time series, which is very similar to what we do in data mining. Great question right there. Thank you for asking, Walker. This is 475 time series analysis, and we were doing a lot of this analysis. I don't think, do I still have it up in the viewer? We were looking over here at different time series patterns and looking through this today. Check it out if you want in office hours. Snea was asking some great question. Data Camps loves using some dplyr pipes. You'll learn a lot about this right here, and it's pretty powerful. Like truthfully, and maybe it'll be over winter break or the summer, I've been thinking about updating this course. It's just we use a lot of what Petri created, which is really great, makes things pretty easy, but there's a lot of really great functions like what was I using today? I'll show you one of the coolest things. If you want to get a lot of stuff for a little bit of work, GG Ally has GG pairs, and we've probably seen this before. I think I've shown it. Oh, is it not? Do I not have GG Ally loaded? I might have reset R. I cannot type. GG Ally. Okay, good. And GG pairs. There we go. And survey 10, of course, right? What else are we going to use? And here's the columns, and watch this. So with just that little bit of code, here's the output I get. So I can look at the heights of males and females, the weights of males and females, the desired weights, the GPAs. I can look at univariate combinations of there were more. I think this is the males. I wish I could see which that was right there. No, I think there's more females than males. Yeah, just wish it would tell me when you turn your R code into a cheat sheet right here. And there are some cheat sheets for each of those. We can see the combinations of these variables over different combinations. Oh yeah, there's gender, height, weight, all these things. And this is all through the GG pairs, which is a more complex way. And last but not least, you could take all of this and just pipe it through a ggplotly. And do we have ggplotly up? We do. And then when you plot that all through a ggplotly, you get the latest version right here of everything with interactive graphics for you to go over. And now with this, we'll zoom in on it. You could actually go over here and look at the 5-number summary for these graphics pretty easily. So you get every little bit. You could highlight points and see each point in the graphics. So all of this can be done here. ggplot is kind of a graphics thing, and then ggplotly is the way to turn a ggplot into a plotly object. So plotly is its own package. So plotly is like interactive graphics. This is now a plotly object, and a ggplot object is a non-interactive. So here you see how this is in the viewer. This is the ggplot version of it, and this is the ggplot, and this is the plotly version. Notice it did have a little bit of trouble converting some stuff, moving around some axes. So I might use this more to look at stuff and understand what's going on with the data. If I'm presenting things and putting in a report, I'm probably going to take a screenshot of this. Like this one looks a little bit better right here with what's going on. It's still a lot of data though, but if I really want to click points and see what's going on, like who's this weird person right here, I can actually isolate that person in every graphic. So it's a pretty good diagnostic tool to do a little data sleuthing and see what's going on here. I wouldn't include this in a report though, because it's a little bit much. We're being Brian here, we're being a little bit extra at times. That's the way it goes. Let's hop back to the main screen. So the idea of RMSE is very important, but we got a problem here. RMSE is the typical miss the model makes. Our model doesn't make typical misses, which means we don't have how far we're off. We don't really have residuals. Someone either has diabetes or someone either does not have diabetes. Does that make sense? So we'll either get that prediction what or what. Someone either, because previously we could do like, how far are we off in our prediction? Like previously it worked like this. How far is my prediction off for somebody? Now our prediction is either right or wrong. Now we're either going to say, we're going to give you a probability, and if your probability goes above 50%, we're going to predict you either have diabetes or you don't. The two things we previously optimized on were RMSE, typical miss the model makes, or R squared. Very similar, because remember RMSE is like typical size of the residual. So it's directly related to R squared, because R squared is the percent of variation Y explained by the variation in X. And if our RMSE were to equal to 0, good conceptual question, then what would the R squared equal to? RMSE equals to 0 means the typical or the average size of a residual, like on average our residuals are 0, then the R squared would equal to 1. Great job, David, right there, because we've explained all the variation. Does that make sense? So conceptually, if there's no miss of the model, all the variation is explained. So the concepts coincide with each other. They are hand in hand working together to do same things. But now we no longer have this because our model doesn't miss. Our model either makes a right prediction or our model makes a wrong prediction. So we'll have a new way of dealing with this. So when we think about this, how do we make predictions? It'd be perfection. Balanced as all things should be. Well, when you're on this balancing point, what we have right here, our model either predicts level of interest or our model predicts not level of interest. Explain to me briefly again, when would something be predicted to be the level of interest, which is the last alphabetical, remember that. So when we predict something to be the level of interest is when the probability from the logistic is what? When we predict the level of interest is when our model gives a probability that is what? It says it right there. Over 50%. Technically 50% are over, and some algorithms will flip a coin. So like the notes say 50% are above, but some algorithms are like, oh, I'll flip a coin right here. Flip a coin, see what comes out. So that's how we deal with it right there. We make predictions, say, oh, you have a 70% probability of passing the class. Well, if you heard the model gave you a 70%, let's say 98% probability of passing the class, I hope it would predict higher than that. But then you would predict what for that person? Random person, 98% probability of passing the class. Yes. Then you would predict what? Passing. And so if the variable is pass class, then the variable will have probably levels, yes and no. And we would be predicting someone passes the class what? So Josh, and good question there, Josh, 100 points. Passing the class is the variable. The levels are yes and no. And thus, so remember, reference level only applies. So let me repeat this again. Good question right there, Daniel, too. And Nathan's right. This is going to be the level of interest. So this is going to be the one of interest. If you say reference level, you are probably talking about what's is. And I always use it for that. Here, that's a Y variable. If you are talking about reference levels, which have a different way of doing it, and those are what's is. This is where we have to make sure we understand, because this is where confusion happens. Like if we were to use this as in a what variable, it would have a reference level. And this is the big change. We're not quite doing this sort of thing right here. But now, this would be the reference. What's the difference right here? So here, I'll explain. So Josh, hopefully I make sense of this right here. Level of interest is always just last alphabetical. Rock?
It doesn't matter.
Probabilities don't matter right now. How we predict it, if we have a probability of 40%, we'd predict not the level of interest. But level of interest is something we assign. Does that make sense? Like, let's predict whether somebody is a freshman or a senior. What would be the level of interest? We're predicting if someone is a freshman or a senior. The level of interest that you can figure it out from that would be what? So we're predicting if you're a freshman or a senior. It'd be senior, correct. That's all you do. What's the last alphabetical? And now our model says there's a 20% probability. So what does that mean when I say the model gave out a probability of 0.20? The model returned a probability of 0.20. Kind of that means individuals over repeated trials, and Daniel, great job right there too. Exactly. The model over repeated trials of individuals with these characteristics, we would expect blank to be blank, thus we predict blank. Over repeated trials of individuals with the same characteristics, the model says what? What does this mean right here? That we're predicting senior's the level of interest. Here's the probability we get. So over repeated trials of individuals with these characteristics, we would expect in the long run, because it's law of large numbers, not like one person, but over repeated trials of individuals with these characteristics, the model says what? We'd expect what in the long run? It's not about one person. Who knows this one right here? Over repeated trials of individuals with these characteristics, the model would expect what? Exactly. In the long run, exactly. Like we would expect in the long run to observe 20% seniors with individuals with these characteristics. So if you have one person with these characteristics, and this is what the model predicts, you'd predict this person is what? You'd predict what? You'd say like, okay, we ran the person through the model. The model says in the long run, 20% of individuals with these characteristics would be expected to be seniors. So for this one individual, I expect them to be a what? And i.e. not the level of interest. Exactly, not the level of interest, which means we predict they're a what? Not a senior, which means they're a freshman, right? Exactly, more likely to be a freshman. Payne, great job right there. Great job, Payne, right there. more likely to be a freshman. The probability of not level of interest is 80%. Does that make sense? Great job, Walker. Not level of interest is 80%. Probability of level of interest is 20%. So you can figure out what's the probability they are the level of interest or probability not the level of interest. But do remember, level of interest is only for the what variable. If I'm talking about level of interest, I'm talking logistic, and it's for the what variable. Exactly. And it's for the y. Great job, Walker. Both answers right there. Levels of interest are for y. If you hear me start talking about reference levels, you're probably also going to hear that there's what other things here. Like once you hear reference, we're talking about certain other types of variables. Because if we use this variable as this, then we'll start talking about a reference level, and we'll also have the other things too. I'll put that up here. If there are references, you'll also hear about indicators. There could be indicators plural if there's more than 2 levels to the categorical variable. So once you hear reference levels, it's all about the x variables. Once you hear levels of interest, it's all about y variables. Does that make sense? Really good, conceptual thing that usually throws people for a loop. What do we say? Logistic, level of interest last, reference level I am first, or the reference level is first with indicators and with categorical x's. Good review right there. So if somebody is actually A, what do you think we should do? Just tell me, if someone's actually A, what do you think would be the right thing to do? Someone's actually A. What do you think we should do? We should predict A. Great job right there, Josh. Yep. If someone's actually A, we should predict their A. If someone's actually B, we should predict their B. So this is what I call the on diagonal. It's the way I was taught it. It's the on diagonal. If you have a bigger matrix, you could have a 3x3. And you'd want it to be right there. Pretty cute. So we have right here the on diagonal, and this is the off diagonal. So there's basically 2 terms for this. We have here our accuracy or classification, and then we also have our misclassification. So pretty easy to see here, what is the accuracy of the model, or how well does it classify things, or what is the misclassification? And what do you notice, Stat 1 terminology right here, about the accuracy and misclassification? Here's the accuracy of the model, found by adding up these numbers, dividing by the grand total. And what do you notice right here about the misclassification of a model? Found by adding up these numbers on the off diagonal, and then dividing by the total right here. It's going to look really weird. So what do you notice about the misclassification of the model and the accuracy? Pretty easy to see. Like, you either get things right or wrong. It's either right or not right. So the accuracy and the misclassifications are what's of each other. And you can call it classification rate or accuracy. Sometimes it makes more sense to call it the classification, like how well it classifies things, because then you can say the misclassification. They're complementary. Great job, Josh, remembering the terminology. They're complements of each other. And so we have right here that you either get something predicted right or you get something predicted wrong. Now, here is where people usually are confused about the naive. The naive would not have any what variables in it. This is a great test question. The naive would not have any what variables in it. The naive has no what's in it. The naive has a y variable, has no x's. Nathan, on fire today, man. You got this. The naive uses the what level of y to make predictions. There are. Great job, Max, right there. Max, follow up answers right there. You got it. We'll talk about that in a second right here. The naive uses what? Not quite y hat. The majority, Wilton sees it right there, the majority level. So most people in this data set, what? Just tell me about most people in this data set. It uses the majority level. So most people in this data set are actually what? Only look at the information being presented to you. Most people in this data set don't have diabetes. So we predict nobody has it. So how many does the naive get wrong? Just tell me how many people. It says, well, most people don't have it, so I guess no one has it. Most people are actually, no, exactly. Most, because we only look at the y. We only know the y for the naive model. So we're going to look at the majority level, and it gets 130 wrong. And that is the misclassification of the naive. Could anyone quickly compute in their head, just use this maybe, what the classification of the naive is? I made it easier. What % of the time is the naive correct? Just making it easier on your life by doing that. I wouldn't round it or do that if I was actually solving it, but that just makes life easier. What is the actual classification? 67%. Yep. So the naive is wrong about 33% of the time, and the naive is correct about 67%. And then we could compare this right here to say 67% right here, and we go up to about 78%. Pretty good increase. Pretty good increase. Pretty good right there. I might do a data mining on this to end class. Here we go with another model. Naive is the same. Does this model do better? This is all two-way interactions. What is the classification on this model? Who can compute the actual classification on this model? What is the accuracy of this model? Ooh, I bet someone can get it really quick. Tell me how you achieved this. What is the classification? Now, you can do it the long way. I'm going to do it the long way. You do it the quick way with the information on the screen. On diagonal, divided by the grand total. And who knows what this equals to? 80.4. How'd you get that, Peyton? Great job, Peyton. 100 points right there. 80.4. Reason being is that this is, and there might be some decimals maybe with differences, but I hope not. Reason being is that these are complements of each other. There's the misclassification, and there is the model itself. There's the classification. What do you notice about this model? It predicts everybody what? Which is the what? This is an actual model right here that is very statistically significant, and it predicts everybody what? The model predicts everybody what? 4 minutes. Will not donate, which is the same as what? Model does no better than the naive. Predicts everybody will not donate, which is the exact same as the naive. We have other ways of doing this with data mining. We'll look at that later. So there's the curve. Never goes below 50%. It says no one's going to donate. Now remember, this model was donate, no. Donate and no is the level. So no is the level of interest because no is last and donate is first. We did the goodness of fit last time. We'll end with this. It predicts everyone's going to be a Scrooge. And then we're going to go do a question right here in a second because I said we would. We did the goodness of fit, and I think that's it, basically. Let's go look at a goodness of fit. Is our model here a good or bad fit? Now, review last class if you don't know the answer to this. And we're going to do a homework question to end class. But is our model here a good or bad fit? Yes or no? Oh, it says the answer. Don't look at the answer. Is our model here a good or bad fit? This is a goodness of fit test under the check regression. I'll remember in logistic, Daniel, level of interest is last. Does that make sense? In logistic, the level of interest is last. Your reference levels is first, but in logistic, the level of interest is last. And people are saying bien is good because the p-values on the goodness of fit are above 0.05 because we assume in a goodness of fit that everything's good till we have evidence it's bad. And Daniel, does that make sense right there? Just to review again, in logistic, the level of interest is last. So we're talking about logistic and whatever is last alphabetical. And so since we have two levels right here and the levels are donate and no is last alphabetical. And by virtue of it being last, that means it's the level of interest. So level of interest. Does that make sense right there, Daniel? We're going to do a question right here. But that, yeah, no, good question. That one's weird because it's not a yes, no. You would think someone would say, does someone donate or not donate? But they put donate. It's just the way they coded their data. So the way it goes. Let's go look at a problem right here. Hop over to the main screen. I always love doing graphic stuff. Who is doing a question right here that they're working on? Let me clear this all out because it's eating up so much memory. Who is doing a question that they're working on right now? And they're like, hey, Brian, could you talk over this? Who's got a question right now on assignment 10 logistic? Which ones are you looking at? We got a lot going on here at the end. 1C3. Let's go look at 1C3. 1C3. And we got right here. Is the interaction between these something we should really be including in our model based on the results of the drop one? Why or why not? Now, I think we're predicting last amount right here. Let's just do all of C. We'll do 1-3C here, and then we might have time for one more after this. So let's go over here. We got to be very careful how we run this. I'm going to throw in a chunk right here to make the model. Now, am I going to use LM or GLM? Be very careful. We're predicting last amount right here, which is quantitative. So am I going to use LM or GLM? Am I going to use LM or GLM? I'm predicting last amount. I already did it. Predicting last amount, which I think is spelled that way. I think we'll find out the hard way in a second right here. Why am I using LM? Why am I using LM? And why? You are correct, Walker. Great job. 100 points right there. Why am I using LM? You're 100% correct. I think it's EX5. No, not donor. We're using census data. Do I have it loaded up? Let me see here. EX4. I thought it was EX4 census. Yeah. Really? It is EX something census. Where are you at? EX5 donor. What? There we go. Good. Why is quantitative? Exactly. Why is quantitative? So we're using the LM right here. I'm going to bring that a new line. Yeah, I don't want that. Okay. And now is something we should include in our model. So when we run the drop one right here, we don't want to look at the summary first. We will, but we see right here that these are statistically significant. And you know what? Probably the quickest way to see if it is statistically significant is to do the visualize, and it visualizes it. So this actually runs the drop one right here for you. So you see this p-value down here of 2.712 e to the negative 10. That's a ridiculously significant p-value right here. And we would get this also via the drop one, including the model test equals to F, and we get the same p-value. Note, and I want to make this very clear, tips for the take home. You can get the p-value for your interaction by running the visualized model. And you notice right here, which of these has the strongest relationship is rural, which means the coefficients of the interactions for these other ones is going to be what? Who knows? I can tell you the coefficients for the interactions, and this one's going to be the most this, but rural has a positive slope, and then these other slopes are what to it? So that means the interactions for these on the slope of recent average amount must be what? So the negative, boom, Walker right there. You got it, man. Yep, and there's the coefficients. We say it's negative because they're less than. It's not that the slopes of these are negative, but here's the original slope, and then you see that the slopes are less. And here is the suburban right here, the red line, which has the greatest difference right here. It's still a positive slope, but it's this much less than the slope of 1.1. Exactly. And then these are differences in the intercepts. The highest intercept is going to be suburban, which looks to be the green line. Is green line no, that's urban. So the red line, suburban's the highest. And we should see that for the intercept. Yep, you can see it right down there. And then suburban's really close. And then rural is the lowest because all the intercepts are higher. Intercept, no one really cares about you, intercept. We care more about the interaction right here. So is it statistically significant? Most definitely. Who has another place for us to go? We could do a little donate right here. I'm going to show you this right here because when you're doing donate, you must make sure that we're predicting donate from total donations. And we're going to store into here GLM. Oh, see, I'm about making some mistakes right here. Donate tilde total donations. Data equals, and will this work? Yes or no? Throw some comments in the chat. And there we go. I like it. I like it. What's going on right here, everybody? I know, right? I make some mistakes in code, but this is a purposeful mistake. So what's going on with this? Someone's like, it won't work. Is broke. All right, let's just switch. Yep. Family equals binomial. Yep. Family equals binomial. And that is when we're fitting the logistic curve. Lots of ways to do the binomial right there. That works. Or the parentheses or the quotes. Let's visualize the model here to get an idea of what's going on. And you can see people with higher total donations have a higher probability of donating. La Familia. Yes, change the La Familia. Only in this instance. And we should see a positive coefficient for total donations because the interpretation of total donations would be two individuals who differ in their total donations by one. The individual with more total donations is more likely to donate. And when would someone be likely to donate right here? I think we've covered a lot of the questions here, but when would someone be kind of like, at what point would someone be predicted to donate? Who knows? We'll end class with this right here, and I'm going to try to do something. Who knows at what point somebody would be predicted to donate for a 500-point total of question of the day to end class? At what point would somebody be predicted to donate? Now, I know you can kind of estimate. I can kind of estimate too. But at what point would somebody be predicted to donate? And the answer kind of exists right here. Boom, I think Justin's got it right now. Justin, great job. We're going to take the negative intercept over the slope. Oh, yeah. Oh, rounds up, rounds up. That's it right there. And amazing work right there to end class. That's got it. Oh, I hit the wrong button. That's got it. Class is over. I'm going to try to do something a little crazy right here. Try to do something a little crazy. I want to see if I can challenge myself in 5 minutes. So if you want to see some of later classes, I'm going to pull up a Shiny app, and I'm going to try to make that thing I was talking about. Let's say Logistic. So I'm going to try to make something right here if you want to check it out. You're welcome, Lindsay. Great work, everybody, today. I'm going to try to build something right here. We're going to see if I can get it to work. Let's see. This is right at the end of class right here. So I've got maybe 5-10 minutes to make this work. So this is Shiny right here. Shiny lets us build interactive apps. I'm going to use this slider right here to use different values, and then we should be able to see the logistic curve change. So all I need to do is build the logistic curve, write the logistic equation. So let's go grab a logistic equation. Like, let's go, we had interactions today. Let's go do the diabetes one. So we're going to make a model, and we need the PIMA data. So we go here to GLM, diabetes, and insulin times glucose, and data equals PIMA, family equals binomial. Oh, PIMA data set's not loaded. There we go, and let's do a summary of it. And here's the coefficients right here. Okay, so the coefficients, let me go options. Digits equals 10. Oh, SciPen, can I do a comma? SciPen equals 10. There we go. Ooh. Digits equals 6. There we go. Okay. So, equation. Intercept plus insulin. There's the value of insulin right here. Plus glucose. And there's that. And let's bring this to a new line right here. And then we need the interaction right here. The only thing I don't know how to do, which I'm going to figure out real quick, is I don't know how to get, there we go. There's my equation. I need to plug in values of insulin and glucose. Oh, saying can't find insulin, right? That's fine. Oh, and then this needs a star. It's mad about that. There's that. Okay, good. And then we need a value of insulin. Insulin equals like 10. Glucose equals like 10. Good. Equation should solve to a number. That's fine. And so now we need to graph an algebra equation. Graph algebra equation in R. So plotting a mathematical formula. Here we go right here. Curve. Okay. From... That's so complicated. I've done this so long ago. Plot this curve right here. Okay. Let's grab this. Let's see if we can get this to work. I really want to see. It's taking 3 minutes so far. So that's my equation. They're doing this right here. Should just plot. That plots that curve. And so now we have this. That's fine. Let's say y is prob yes. X value is insulin. And we're going to go insulin from 0 to 20 by units of, n equals, it took 300 samples. That's what it did right there when it made that curve. This is how many observations it's taking to make the curve. That's cool because it's actually having to do it. Line with blue, all this other stuff's great. Let's make this look a little bit easier to read. From to by, labels. And then we've got the colors right here. I don't think it's on a different line, but let's put it on a different line. There we go. And the main title right here. Good stuff. Okay. Now we got our curve nice and sectioned off, easier to read. And now we need to take our curve and do the same thing where we have the value of x being used right here. So I think it wants like insulin to be like the x. So here's our equation. And we already have this equation written out. I don't think it'll work if we just drop this in right here. So if we drop this in, it's not going to like this. It got mad. And it must have an expression containing x. That's what it wants. So right now, and we have values of insulin, so we got to be careful right here. We need to take, and we need to do a solve on this. Oh, here I have it. I'm not good. Oh man, it's gonna be a little more complicated, I feel. because I almost need to write it out and do an equation right here. Oh man, so close, so close. You know, they're like, okay, so if I were to plug in values of insulin, let's go right here and go to, okay. So we need, it wouldn't be formula. Can I do a paste on this? I just might paste it in his words. We don't want that. No, if I paste it in his words, it should be fine. Let's go to paste. And let's take this right here. And this right here is what we're going to paste. This needs to be in quotes. Got really complicated, didn't it? And then, okay, so we're going to solve for values of glucose, let's say. And so the values of glucose we need to solve in here. We take this, comma, and then we open up the second thing right here. Oh, we don't, because we're solving for values of glucose. So we put this right here. And then we put a comma. And then this needs to, actually, we can go right here then. There, comma. And then the value of glucose we get will be chosen for us by when I assign the glucose value, comma, parentheses here, comma, and there's that. Okay, now if I have a value of glucose solved in here, okay, good. Let's do a \n. No, oh, it's seeing my \n right there. It's actually doing that. I didn't even know that. We don't want those \n's in there. It's seeing that I pulled a new line. It's actually, I didn't even know it would do that until I saw that right there. It's calling my new line code because it saw those. Okay, so here's our equation. And now we need to call insulin X, because that's what it got mad at me about. It said, you don't have an X. And so there's our X right there. And so that's the value of X right there. And let's call this formula. And let's go here to formula. Could not find function formula. Oh, did I not run it? Ooh, doesn't like that. Would it use this? So close, we're getting close. I want to see if we can get it. All the coding we can do. So this right here, would it use it if it was proper? So the value of glucose, let's just plug in, we'll just plug in like 0 for it for the moment. And we'll see if it runs. That's the value of X. Okay, there we go. That's got it. Unexpected quote. Oh, that extra star. Okay, we got something. We got something. Because now it needs to be e raised to the over 1 plus e raised to the exp raised to this over 1 plus and then exp raised to this also. And now we're seeing a slight bend of the sigmoidal curve right here. So we're getting there. It's just I have to change the value of the equation. This is the whole problem we're running into right here. We could probably run it like this, and that looks a little bit better. Error figure too large, that's fine, because I made it small. So now we have this right here. We just need to change the value of the equation and plug in numbers right here. Oh, I think we can get this done with the shiny so easy. So I think we're basically there. Because right here is the insulin value. I think the shiny is actually going to make this nice and easy. No, wait, where's the insulin value? I deleted it off. Okay. Let me go look at the equation again. I'm so close. Let me go back in time right here. Let me go forward in time. Okay. We're so close. E raised to the... There's the coefficients right here. Okay, there's all the coefficients. Let me look at the summary of the model again. And and then we took off the insulin here. That's what we took off. So we need to do input times input $insulin right there. Is that? No, that's Oh, wait. That is the variable itself. So that is our first variable right here. And glucose is what's changing, I thought. So let's change the glucose right here. Glucose is going to be X. And then this right here has the X on it and times input insulin. And then we're going to change the value of glucose right here because there's the coefficient of glucose. Okay. This should work with the input $sign insulin. Okay, we've got a good shot at this right now. Here's our curve right here. And we should be able to go into here and go to render plot. Got all this great stuff right here. And I hope it takes the curve. Should test it out to make sure it takes the curve right there. And that's got that. Now we're going to go here to input. And we've already got an input right here for the bins, but we're going to change the input to insulin. And let's say value of insulin. And that's fine right there. I think we can do value 30. That's fine. Min, max, all that good stuff. I feel like something's wrong. It's too easy. Input not found. Run logistic. Input not found. Where's the... Why is it mad about? Oh, I know what it's mad about. It's probably mad about all this up here. We're getting close, but I don't know if it's going to happen in time. Ooh. Oh, it's not changing. I don't see the curve changing. We have something, and the numbers are changing, but I don't see the curve changing. We're so close. We're so close. We're so close. And that's the expression right there. I think we need a reactive expression. So I think that's the issue. Reactive. Let's call this react express. And we need to take this expression right here. And we need to drop it into here to make a reactive expression. That should do it. And now we need the react expression, which will change. And that'll open up there. Let's run it. Expression must be a function or call the same containing X. It is. It's a reactive. How dare you tell me that that's not a function? That should be create reactive expression. That's so close. Is it just mad because it should actually change it with the inputs, no? Input insulin should be changing that. It should update the curve. I am shocked. It's updating the numbers on the curve, which is so odd. X is missing with no default. Oh, okay, wait. The input insulin... Okay, I have an error. I think this is it. Because we're inputting glucose. And so this is how it changes. Okay, no, we want the X to be there. We just had it work a second ago. So close. Oh, is it mad? Is that what it is? It running the app but then giving the error? Oh, wait, I did a moment here. So close. So close. It's updating the axes, which is so weird. From 0 to 20 by this. It's updating the Y. It's just not redrawing the curve, which is driving me nuts right here. So close. Try like one more minute. Because the input insulin should be resolving the equation, but it... Maybe an observe on it? I'm going to try something crazy. Last try. If it doesn't work, it doesn't work for now. Probably not going to work. Now it doesn't even draw it. It is changing the axis, though, it looked like. It did a little change right there. That's so weird. It doesn't do a plotly. It doesn't like the plotly. Might ask people during office. I'm like, okay, why is it not working? We're so close. Change with interaction. Well, we'll figure this out. We're so close. We got the plot going, but we're just so close, but yet so far. Till then, we'll see everyone later. I'll figure this out. We'll figure out what's not going wrong, what's going wrong here. Bye for now, everyone. Bye.